So in the practice of science, we have investigations that are conducted to explore new things, to check on previous things, to test how well theories predict, and to compare different theories. And so that's why we conduct investigations. We have very strict standards for scientific investigations, and so we we have to have that, because we want our result, or we want our experiments to be valid. Theories are never set in stone. We can have new and better models, new and better theories that come up, and so when Einstein proposed the special theory of relativity, it took some time because it was a very, very different way of thinking, and we accept it now. And scientists must be aware of their own bias, and so scientists can have, can really want results, and if they're not careful, have a temptation to compromise the results. And new ideas in science usually grow very slowly and from many contributors, and so it takes time for new ideas, for new results to be accepted. And if we think about a theory, these are how they're judged. They're judged by how well they fit other theories. They have to explain. That's the key word. Is theories explain why, and how they explain the observations, how effective they are in predicting things. And so this is how we judge theories. And for instance, the special theory of relativity has to fit with other theories. It's got to explain things well. They have to explain what we observe, and they have to be effective in predicting, and the special theory of relativity has done that. Now, laws describe things. That's the key word. Laws describe what's happening. They don't try to explain, so do not offer explanations for those relationships. So theories are well-supported explanations, and laws are well-supported descriptions, and this is a good way to think through that. And scientists, operate on the belief that rules of the universe can be discovered by careful study. And we're thinking about the Large Hadron Collider in this unit in the study at CERN as our case study. And that's the fundamental belief, over time, that we can figure out how the world works and how things work. It's important to report what is found, and so even if there's unexpected things, it's important to report them so other scientists across the world will know, and they might be working on similar things, and it could help them out. Peer reviews, where the peers of the scientists, people that know what's going on, can review their work and give critique. And sharing with the public is also very important, and so we do that through journals and through conferences and the internet. Systematic and random error is very important as we consider our labs throughout the year. And so there are two different kinds of error. And these are not mistakes made by the individual. That's experimental error. So if you or someone in your group makes a mistake, that's an actual experimental error. Systematic error causes a random set of measurements to be spread out about a value rather than being spread about the accepted value. So systematic error, you can think it has to do something with the system itself. Let's say that you have a balance, right? You have we'll say like a triple beam balance. And you place something on the balance. And let's say it's consistently off. Let's say it's consistently off by 3 grams. Well, that's because the balance itself is messed up. You as the experimenter did fine. You didn't make a mistake. However, everything that you measure is exactly 3 grams off. That's a systematic error. Now, a random error is where you have outliers. And so this is as you're doing an experiment and you have something, you have most of your data. Let's say this is a data plot, and you have most of your data is pretty good. And then let's say you have an outlier out here, another data point down here. And random errors can be caused by different things as well. Can be caused by some of the things in the experiment, how it's set up as well. And But with the systematic, it's consistent. With random, it's going to be, outliers where most of it is actually good. So when we talk about precision and accuracy, they're two different things. Quite often we can interchange those words, but it's important to distinguish them. In terms of precision, precision is how precise you can get it in a measurement. So in other words, if you're measuring something, how exact can you make it? And, how many decimal places, beyond, well, not necessarily decimal places, but how many values can you get to measure? And so for instance, like a meter stick, we have the tick marks, right? And each tick mark represents a millimeter. But, if you get a device where it's like this, where you can actually clamp down on it, you can get much, much more precise and get a value that is much closer. Now, accuracy is getting close to the accepted value. So the accepted value. So accuracy has to do with what it should be. So if we think about these things here, let's say that we have some data points that we've got, and let's say in this case here we have these data points. Now these data points aren't close together, so they're not very precise, and they're not very close to the target. The target's right here in the middle, and even if you average these, they're not accurate. In this case, we have accuracy but not precision, right? These values are very spread out. As you took these measurements, let's say it's of like a meter stick taking a measurement, or something taking a measurement of a length, and they're spread out about a value. If you average them, you're going to get pretty close to what it should be if you took all four values. Now, on this one down here, there's probably some systematic error because you're getting values that are close together, and so they're precise, but they're not averaging to be what they should be. And then the last example is where the values are close together, and then also they're where they should be. So an example I like to use in classes, what they did a few years ago is they took these neutrinos and they shot them many hundreds of miles underneath the ground. And they measured, they were pretty sure how long it was, they knew how much time it took, and they thought that these neutrinos actually went faster than the speed of light. So they thought they were here. They thought they had something very precise, because their measurements are very precise. You can get really good values, and they thought they were accurate, but they were actually here. There's a couple errors that they had that they couldn't find. Had to do with the cables in there that were off, and so they weren't getting the correct value, which was slower than the speed of light. The neutrinos actually didn't go faster; they were slower. And so once they fixed the system, they did get here, and they found out, okay, well, these neutrinos they're going fast, but they're not faster than the speed of light. So when we measure using a meter stick, what we do in terms of measuring, we need to consider the limit of the reading. So in this case, the limit of the reading is 1 millimeter, or 0.1 centimeters. So, each of these tick marks here represent a millimeter. So what we do is we would say the uncertainty then is plus or minus half of that value. So let's say we measured this block, and let's say we measured it and it was exactly 2.2 something. Well, what we have to do is we have to guess to that next digit, because we can know that it's going from here to here. We're looking on here. We know it's beyond 2, but not quite to 2.3, and so we have to guess to that next digit, and then we say, okay, we're plus or minus that 0.05 value. The reason we're plus or minus 0.05 is because we may not be exact on either side, right? So we're going to try to line this up perfectly, to measure, but we're not going to be exactly on. So this is a conservative way to do this, to give your reading and uncertainty, and that's what we're going to use for our class. Now we're going to talk about calculating with uncertainties, and this is a really critical part of the IB program in terms of the labs, and how we compute the data that we get to be able to get something realistic. And the example that we use in the class is the one with a metal bar. And if it's beyond a certain volume, the machine's going to blow up. And so we have to know, if we measure the length times the width times the height of something, and we get a certain value, it's plus or minus what? So how precise are we saying this value is? And then we can make decisions based on that. So up to this point, most likely you've just concentrated on getting this value, but we really need to focus on this as well. Okay, let's take an example of multiplication. So let's say that we have two values here. Let's say we have a value of W, which is 4.52 plus or minus 0.02 centimeters. And let's say that we have a value of X, and that value is 2.0 plus or minus 0.2 centimeters. And let's say that we want to get the area, and the area is going to be W times Z, or W times X rather. And so what we do with this is we use an equation of, and this is you don't have to memorize this. This is on your IB equation sheet. The uncertainty in Z over Z is going to be the uncertainty in W over W plus the uncertainty of X over X. And how we get about this, we're going to gloss over a little bit here. When you take statistics, this will, you'll see how we get this, as we take a look at standard deviations and that kind of thing. And so, what we want in this case, W times X, if we actually just calculate that, that's going to be, 4.52 times 2. And in that case there, we get 9.04. But, and that's centimeters cubed, right? But how precise is that? It's plus or minus what? How much bigger, how much smaller can it be? And that's where we're going to need this. Okay, so let's do that. We're going to take these values, figure out how we get that. So the uncertainty in Z is what we want over Z, so that's 9.04. That's what we just did right here when we calculated that, is equal to the uncertainty in W, which is 0.02 over what W is, 4.52, plus the uncertainty in X, which is 0.2 over what X is, which is 2. And then our next step will be actually calculating that out. So 0.02 divided by 4.52 is 0.004425. You could keep the value in your calculator, and then you're going to add that to 0.2 divided by 2. So 0.1 plus 0.1. And so we end up getting 0.104425 is the uncertainty of Z over 9.04. And so when we put this over 1, we'll cross multiply, and uncertainty of Z comes out to be we multiply that by 9.04. We get 0.944. And and so what we do, again, we'll round to one significant figure, so to 0.9, and that's what we've got. So in this case here, the final answer would be we're 9.0. So again, going back to our rules here with the number of significant figures here, we have 2, 9.0 plus or minus 0.9 centimeters squared, which is much better, because now we know that it's either it could be all the way as big as 9.9 or as small as 8.1. And so this means a whole lot more.